solution proceed Cu2Mn SNS4 thin films for non-volatile memory devices.
Hello. Good afternoon, everyone. First of all, I would like to thank the organizing team of Presision for giving me the opportunity to present my work, and by offering my sincere pronoun to all the esteemed dignitaries present here, I would like to start my presentation. So, in the presentation, the topic of today's discussion is exploring resistive switching in CMTS thin film for non-volatile devices, memory devices. Now, there are maybe some unfamiliar terms here. Now, like resistive switching, like non-volatile memory devices. So, don't worry, we will come to these terms and we will understand this term very deeply. So we all know the term memory, right? So we all use this term very often. He has a very bright memory, or compute the memory of a computer. So let's first understand how does the memory of a computer works, or how we store data in a computer. So suppose I am storing a data, I am taking the data as 9. So what the computer does, the computer sends the data to its CPU, or more specifically in the arithmetic logic unit. So in the arithmetic logic unit, the data is converted to its binary form. Okay, so now, and when we assign a particular memory location to this data, the data will be transferred to that location and the data will be written here. So the interesting thing is that be it a number, be it a picture, be it a word, the data will always be converted in its binary form. So, and the binary form consists only 1 or 0. So to primarily to make a memory device, we need only two configurations. One is to store 1 and one is to store 0. But the question is, how does a computer understand what is 0 and what is 1? After all, it is electronic circuit, right? So how does it understand? So if we go deeply into this, we will find that a computer does not understand any 0. What does it understand is the difference between its physical electrical components, like high voltage or low voltage, like high resistance or low resistance, or presence of current or absence of current. So by differentiating these terms, we design 0, we assign 0 or 1 to the memory devices. Like in transistor, if there is current, this configuration we call this configuration is used for 1, and if there is no current, we call this configuration as 0. And if we dive deep into the memory, we can see that there are two types of memories. Like one is volatile memory and one is non-volatile memory. So ones are volatile memory. So if we remove the power and if the memory get erased, then these types of memories are called volatile memory. And if we remove the power but the memory is still there, we call this type of memories as non-volatile memory. And we have a very famous example of it, like SSD. We all have SSD in our computers. Now, let's come to the main one, that is resistive memory. As I said, in transistor, we use the current component. So when there is current, we use this component as 1, and when there is no current, we use this component as 0. In resistive memory, we use the property resistance as controlling unit. So what we did, we can see this graph that it is a very simple experiment. We connect our device and we vary the voltage from let's suppose it's minus 1 volt and let's suppose it's plus 1 volt. So we are varying the voltage from minus 1 volt to plus 1 volt, and we are studying its corresponding current. So when we are studying, we are from minus 1 volt to plus 1 volt, we are seeing that the current follows the red curve. Now a very peculiar thing happens. After reaching a certain voltage, the currents rise abruptly and it comes back in a very different path. So while going from minus 1 volt to plus 1 volt, it follows a path, but while coming from plus 1 volt to minus 1 volt, the current path is completely different. And we can see a very steep rise of current here and a very steep decrease of current here. So this is how this property as memory. Now you can see that at this voltage or at any voltage there are two states. That is here the resistance that is the current is very low. So we are calling this as HRS or high resistance state, and this state we there the current is very high. That means the resistance is very low. So we are using this state as low resistance state, and we used to store 1 in the low resistance state in this configuration, and we store 0 in high resistance. Now there are a few terms you need to understand to understand the resistive memory more broadly. So there we can see at a certain voltage the current is rising abruptly. This voltage is called V set, and the process is called set process. And at this voltage the current decreasing abruptly, and this process is called reset process, and this voltage is called reset voltage. And also there is a read voltage. So by putting this voltage we examine the device condition. Is it in LRS or is it in HRS? Now let's come to the mechanism. How does this happen? So we'll understand the mechanism by our prototype. So what we have done, we have made a precursor of CMTS, that is copper manganese tin sulfide, and we made a spin coating of this on a FTO coated glass, that is fluid to tin oxide glass, and this is our schematic diagram. That is a FTO coated glass, and on this we have spin coated CMTS, and on this we have silver. And this is the XRDN round that confirms that we are actually dealing with this kesterite phase, or we can CMTS we are actually dealing with. And also we studied the property of the junction, and it gives a very good Schottky junction, and the rectification ratio is also very good. And the device, so let's come back to the device and study the device. Okay, so our device is mainly three part. Number one, that is top electrode. In our case it is silver. Number two, that is switching medium. In our case it is CMTS. And number three, that is FTU or FTU coated glass, that is our bottom electrode. And two important phenomenon here taking place, that is set process and recess process. So let's talk about the mechanism of set process. So in set process, what we are doing, we applying positive voltage in the top electrode and negative voltage in the bottom electrode. So what happens? There are many grain boundaries inside this material. These grain boundaries act as a trap center. So when we are applying the voltages, some of the copper ions get trapped in the grain boundaries. And while coming to the bottom electrode, due to the electric field, they collect free electron and deposit there at copper atom. And they deposit one after one after one, and at a certain time their deposition reach the top electrode. Now there is a very interesting thing. As we can see, the copper atoms, we have a bridge of copper atoms, we have a filament of copper atoms, and these copper atoms have very large number of free electrons. So the conductance rise abruptly. That's all. This is the mechanism of V set. Now the opposite mechanism is V reset. So what does this in this process takes place? So when we are applying positive voltage to the bottom electrode, the copper atoms get energy from the applied voltage. So it ejects electron, and the electric field also push the copper ions from the bottom electrode to the top electrode or anywhere. So that's how the copper atoms are converting into copper ions, and the bridge gets abducted. That's how the reset process takes place. We also can understand the set reset process. Okay. We can also understand the set reset process by the conduction mechanism. So we know there are three types of conduction mechanism that happens in a dielectric or a semiconductor. So first type is ohmic conduction, in where the I is proportional to V. That is number two is trap charge limited conduction. In there charges started to break trap inside the trap centers, and then when the trap centers are full, then the space charge limited conduction takes place. That means the current rises again. So this is the IV graph, and this is the log I versus log B graph. So when the M, that is slope, is near equal to 1 or 1, it is the ohmic conduction. when it's greater than 2, it's the capture limited conduction, and when it's when it is equal to 2, it is the spatial limited conduction. So if we look at this graph, we can easily see that from ohmic conduction, the trap centers are open, so the capture limited conduction dominates here, and after the traps being filled, we see the spatial limited conduction taking place. So we also did the Schottky analysis. The Schottky analysis is a tool by which we can easily determine the series resistance and the series resistance and the Schottky barrier from couple of equations. And from this, we have studied the high resistance state and low resistance state. In high resistance state, we see the Schottky barrier is 0.89 electron volt, and low resistance state, the Schottky barrier is, we can see that it's 0.62 electron volt, and the series resistance is also decreased very abruptly while in the low resistance state. So in the high resistance state, it's the order of 20,000, and in the low resistance state, in the order of 100,000 ohm. We have also did the endurance test. That's when we have run the cycle again and again and again, and we did it for 25 times. And the pink ones are the resistance of the high resistance state, and the blue ones are the resistance of the low resistance state. And we can see a fair amount of difference between the high resistance state and the low resistance state. So the benefits of resistive memory, that the required voltage here is very low. The whole process takes place between one. So the whole thing takes place between -1 volt to +1 volt, and the integration density is very high. That we can input a lot of devices in very small place, and the fabrication is very simple. And our future goal is to stabilize the device performance, to study the endurance and enhance the performance. And these are the my acknowledgements, our group, and thank you all for attention.
So, is there any other materials you have
resistive switching? Yes, sir, there are a lot of material that shows resistive switching, mainly the some oxide material like TiO2. The oxide materials generally show resistive switching. So, but these CMTS or CZTS, that are generally known for optoelectronic devices. So these types of elements currently recently draw the attention of the researcher because it shows the resistive property also. So there are lots of material that can show resistive. Sorry, sir, I don't have.
Okay, Suman, can you go to your IV characteristics where you flowed?
Yes.
And you are talking about these three regimes, the ohmic regime, and then
the
slope, right?
Yes,
equal
yes,
to 9.51.
Yes. So
okay, so my question is that what happens? Is it just you are increasing because the voltage goes from what? -1.2 to -1.6, and then you see this steep slope, and then it goes to -0.3, and then again your slope changes as you are saying. What is the physical mechanism that is determining that how because after all current is movement of electrons and all that. So what is the physical mechanism that is changing your ID characteristics? Did that make sense?
Ma'am, I think you are asking the mechanism of changing the current so abruptly, right?
So the mechanism of why the IV behavior, why do we see Ohm's law? First question. Why does I goes linearly as V? That's Ohm's law, you are saying. So similarly, why does it go to the power 10 or something? Or 10 times V. So why is the slope changing?
Okay, so you are asking the traction limited conduction mechanism, and
yes, it's all linear.
Yes.
The slopes are changing. So
yes.
There must be some physical effect.
Yes.
What is that?
So, ma'am, so when we increase the voltage, what happens? The electrode also injects some carriers. The electrode, when we suppose we have silver electrode, so when we are giving enough voltage, some silver atoms may leave electrons and get ionized and come into the material. So now what happens if there are a lot of traps? The silver atoms get trapped into the drain boundaries, mainly the trap centers. So that's why, and after when we at a certain level we are increasing the voltage, after one by one the trap centers are getting filled. So when there is the so there will that's why the current is rising so much. That's why the trap centers are open. So the silver atoms get attracted to. Also there is the as we increase the voltage, the positive voltage also pushing the silver atom, so that's why they are being trapped. Yes, yes. That much high voltage. Yes. It's happening because of the electrodes. Because no, there may be this much of rise because there are also the ions that are in the material. So the copper ions and the silver ions that's getting trapped. That's why the rise is so much.
Any question?
Then just a small question that although we are using very small voltage, but the resistance in some cases is going to very high, like for example 30 k ohm or something. Is there a heating issue or some kind?
No, the resistance. So you are talking about, I think.
I may have misunderstood that. So,
In this, no, it is not the resistance. It's a Schottky analysis. That means the first equation you know, right? This is the ideal. This is a diode equation. So if you manipulate this equation a little bit, you will get two linear equations. That is dt and that is HN. So in the equation you can see that there is RS, right? So these RS represent the whole resistance, not only the material resistance but also the surface resistance also. So these all types of resistance is considered as a series resistance. So the resistance is that much is that's why the whole resistance of the material actually. No. There is a heating issue. There is a heating issue. As we see, you can see that the slope is minus. So it is a example of negative differential region. Okay. So here a phenomenon called Joule heating takes place. That's why the filament also gets ruptured. In the reset process, we can also see that. So there is that's why the slope here is minus. So we are increasing the voltage, but the current is decreasing. That's why the heating process is there. Oh no, log minus 1 is equal to 0, right? So we can't take log minus 1. We have to take log absolute value of minus 1. Yes. Ideality factor means how ideal the diode is. Importance, if the ideality factor is near equal to 1, then we can say that the diode is very ideal. There is no there is the junction is very good actually. The PN junction is very good from. That's why the ideality factor.
Okay, thank you. I will